Good morning. So this is a session on probabilistic programming. My name is Jeremy Seek. I'll be your session chair this morning. And we've got 5 talks this morning, each 20 minutes. So if you're doing 15, 16, 17 minutes talk and then a few minutes of questions, we're getting just a tiny bit of a late start here, but not too bad. And so without further ado, let's hear about bit blasting from Poorva Garg. Thank you.
Thanks for the introduction. Hi, everybody. I'm Poorva, and today I'm going to talk about a new way to reason about probabilistic programs. And this is the work done in collaboration with Stephen, Guy, and Todd. So let's get into it. So probabilistic modeling is a very widely used tool in a lot of scientific communities. Scientists use probabilistic models to account for uncertainties all the time. And to make this probabilistic modeling fast and accessible, they use probabilistic programming languages. So what are these? These are languages that support easy creation of probability distributions and allow you to compute over them. So I have an example here of a probabilistic program. I'm defining A to be a Bernoulli random variable. And then, depending on the value of A, I'm defining B, which can be either of these normal distributions. And now you want to know what's the resulting distribution of B. And finding that out might involve some calculation that looks like this. Now, this is a simple program, and that's why this calculation doesn't look as complicated. But for more complicated programs, this might not even be possible in closed form. So we want to automate this part, and that's the primary analysis task that you want to do on a probabilistic program, and it is known as probabilistic inference. Cool. Now, if people must have noticed, this program has both discrete and continuous distributions. For the rest of this talk, I'm going to refer to these programs as hybrid probabilistic programs. And such programs occur very naturally in numerous real-life applications, in computational biology, in modeling clicks on a web page, in modeling supply chains, all the time. And now you want to do inference on these hybrid programs. But unfortunately, the inference for such programs is not well supported. To give evidence for it, I'm going to talk about different approaches of inference that we have today. We have I'm going to talk about 2 broad classes, the first one being approximate sampling-based algorithms. And within that, we have Hamiltonian Monte Carlo, which is a very popular algorithm for doing inference, but it has limited support for discreteness. It doesn't support discrete random variables. Then we have other algorithms like Markov chain Monte Carlo and sequential Monte Carlo, and they are universal algorithms. They can support any kind of programs with discreteness, continuity, no issues. But it has well-known scalability and accuracy issues, because of which HMC came into existence in the first place. Moving on to the second class of exact symbolic algorithms. The first one we have here is based on algebraic evaluation. It's called psi. They take a probabilistic program and convert it into an algebraic expression that they try to solve. And as I said earlier, the closed form of programs do not always exist. And then we have knowledge compilation-based PPLs, such as DICE and Problock, but they do not support continuous distributions. So to overcome the limitations by these tools, we propose a new PPL. It's called HyBit, and it's based on a new symbolic approximate inference algorithm. And it's based on a new form of discretization. What it does is, actually what using HyBit API user can do is they have a HyBit program, and they can obtain a discrete abstraction of it. And once they have the discrete abstraction, which is actually a discrete probabilistic program, HyBit performs exact discrete probabilistic inference on it. And as I showed earlier, there are tools out there for discrete programs. We can directly use those tools. An important thing to note here is that the only loss of fidelity in this process is coming from discretization at this step. So, okay, discretization seems like a cool idea, but it comes with a trade-off. So let me explain this with an example. We have a uniform distribution here. And here I have discretized it into 8 points. Okay. Now I want that discrete distribution to be faithful to the original continuous one. So for that, you need a very large number of points. 8 won't do it. So if I am going for a 32-bit discretization, 2 raised to the power 32 points, then I have to represent 4 billion points. And that's what existing approaches are doing and failing to scale. So to overcome this trade-off, we introduce bit blasting, which is a binarized view on distributions. What we are proposing is take a continuous random variable and approximate it using a distribution on its binary representation. Okay, so how does this help us? You have just changed the representation. You still have exponential number of points to represent. What it does is it exposes useful structure that was opaque before. And that leads us to our first contribution. We have found a class of very common distributions, uniform, gamma, Laplace, that for these distributions, when you represent them in binary, you get a representation that's linear in the number of bits. And that's also without any loss of accuracy. You exactly get a representation of those 4 billion points. To be more precise, if you start with a mixed, I didn't define mixed gamma. So we are characterizing all these distributions as mixed gamma distributions. So to be more precise, when we start with a mixed gamma distribution, let's take uniform for an instance, and you naively discretize it, you have to represent 4 billion points. What I'm saying is, if you bit blast it, you would get a representation which only uses 32 coin flips for 4 billion points. Isn't that exciting? Okay, so now moving on, this succinct representation does not automatically imply efficient inference. Inference, in fact, is sharply hard for these programs. But we also found that when you take our representation and try to do inference on it, you get polytime inference. It's like dream of discretization come true, where we have reduced these distributions from like sharply hard to polytime class. And then we took these theoretical contributions and built a PPL around it. It's called HyBit. It's available on GitHub on this link. It's open source. So what HyBit API does is it allows users to write their programs as bit-blasted abstractions. You can, if you have a mixed gamma distribution, you can bit-blast it exactly. If you have some other distribution, you can bit-blast using piecewise approximations. Here I have a 5-bit approximation of normal distribution. Okay. So now I'm going to go into more detail of each of the contributions that I just enumerated. Okay, so recall contribution 1. I showed you distributions that have succinct representation. So to give you intuition about that, let's start with the most simple distribution out there, which is a uniform distribution on unit interval. Okay, and what we are doing is we are discretizing it using 3 bits, which means discretizing it into 8 intervals, and it looks like this. Okay. Now, if you were to do naive discretization, what would you do? You would flip a coin with 1/8 probability, output the first point. If it's false, you move on to the next coin, flip it, and you go on like this. So you have 1 coin flip for each interval, and that would need 7 coin flips for 8 intervals. What we are proposing is exploit the binary representation. If you exploit that representation, you can represent this distribution only using 3 coin flips. What you can do, you can flip 3 coins, each with bias half, And each of those coin flips would correspond to each bit. And if you are trying to calculate probability of one of these points, you can just multiply them and get the desired answer. And now, once you have this representation, you can just discretize x using 32 bits in 32 coin flips. OK, so uniform was a simple one. Can we go beyond this? And actually, this person from 1970 showed that you can do this for exponential distributions as well. You can have independent bits and discretize exponential distributions. So here I have the program corresponding to this discretization. It looks very similar to what a uniform would be, except the parameters of the coin flips are different now. And these are closed form. You can calculate them, and you can extend this to 32 bits very easily. OK. So these programs were trivial. They were just independent bits. And we don't need to restrict ourselves to only independent bits. We can do, as long as we can have probabilistic programs over the small number of coin flips, it would be fine. So if I start with another example, I have this gamma distribution here on these parameters. And this is what it looks like. Fairly complicated. How will you get the smoothness? And we found that it can be represented using this continuous program that uses uniform and exponential. And we know we can do uniform and exponential. So in the end, when you discretize it, you get a program that looks like this. And this would give you this discretized representation of a gamma distribution. So if you look at this program is using 3k plus 1 coin flips, 3k in the first 3 lines, and then 1 here. And now, as you increase the number of bits, you can just increase that representation to more number of bits, and you would get the corresponding program. So again, if you were to discretize to 32 bits, you just need 97 coins. We were very surprised when we found this. OK, so I just showed you guys how these mixed gamma distributions can be represented succinctly. But how does that help us in inference? It helps us in inference, specifically knowledge compilation-based inference. So let me give you a bit of a background there. So what knowledge compilation-based inference does is it takes a probabilistic program and compiles it to a data structure. What's the data structure? It's a binary decision diagram with the weight function. And the problem of probabilistic inference is cast as a problem of weighted model counting. And it turns out weighted model counting runs in time linear in the size of the BDD. So if I can get a small BDD for a probabilistic program, I can do efficient inference. So that's what we have shown. We have shown that for mixed gamma distributions, when you compile them to BDDs, you get a representation that's you get a BDD that's polynomial in the number of bits. So take the example, the simple one that I showed for uniform distribution. And when you compile it to a BDD, it looks something like this. For each coin flip, we have one node in the BDD. And each of the B1, B2, and B3 are representing bits. So B1 would be 1, depending on whether F1 is 1 or not. And these are the weights. So as you increase the number of bits, the number of nodes would increase linearly, and you would get a poly-size BDD. Yes. OK. So great. What did we further do with these theoretical contributions? We built a PPL. And as I said earlier, it has an API that allows users to write bit-blasted programs. We provide them with a function called bitblast, which takes the bit width, any continuous distribution, the number of pieces, and the range as input. And then we have specific API for bit-blasting mixed gamma distributions. And what this returns is a fixed point number which is a discrete structure. And HyBit also supports fixed point arithmetic. And then we evaluated it on a comprehensive suite of benchmarks. We reported absolute error achieved within a timeout of 20 minutes. We compared with 4 different classes of PPLs, which I described earlier. And HyBit supports all the benchmarks, and it gets the best accuracy on 11 out of 19 of them. So with this, I conclude. What I have talked about today is that how the dream of discretization is coming true, how we have these class of distributions for which we have succinct, exact up to bit width, and exact up to bit width representation, and that also exhibits polytime inference. And then we have built a system around it. So yeah, please feel free to check out the paper and the implementation. Thank you.
Go ahead and step up to the mic, please.
Yeah.
Thanks for the great presentation. So in the translated probabilistic program that you had, basically you had also that one.
Yeah.
So you have basically a comparison operator, which seems to be on the integer distribution. All right?
Yes. So once you have discretized them, you have fixed point numbers.
Yeah.
And then you can do this comparison operation on fixed point numbers.
Okay. So is this the only operator that you use on fixed point numbers, or there could be through the translation usage of some other operator?
So for mixed gamma distributions, we only need comparison. But if you have more general programs, we also support addition, subtraction, all the arithmetic operations out there. So you can write any arbitrary HyBit programs in the general language. But for the mixed gamma distributions, this is the only operator we use.
Okay, thank you.
Yeah.
Did you experiment with bases besides 2 for the discretization, like using like base 3, so instead of a coin flip, it would be like a 3-sided dice?
We did not. We only compared with binary representation, though it would be an interesting experiment to see how the representation extends when you have a 3-sided dice. My conjecture would be that it would only be a polynomial decrease in the representation.
Thank you for the great talk. So what are your sources of inaccuracy currently?
So for the mixed gamma distributions, it's only when you are discretizing them. So it is not representing reals, it is a fixed point number. But when you have more general programs where you are adding and doing arbitrary operations, there you would get any error that would be coming in like fixed point arithmetic.
Okay.
But as you increase the number of bits, that error reduces.
And also in these flip operations for approximating, for discretizing exponential distributions, is there any loss in?
There's no loss of accuracy there.
Thank you for the very nice talk. So basically, when you discretize your distributions, you basically get the probabilistic program which approximates the output distribution. I was curious, in the case of mixed gamma distributions, can you get some basically formal bound on how far away the output distribution of the new program is from the output distribution of the original program, perhaps as a function of the number of samples?
So it's exact up to the b bit width. So if you take the original continuous and discrete, so I have the commuting diagram there. If you take the distribution and you discretize it, or you go through this other route of bit blasting them and then going there, you get exactly the same distribution.
Mm-hmm.
There is no trade-off to make here.
And compared to the original continuous distribution? Before any discretization?
So compared to this one.
Yes.
So the error would be whatever you would get when you discretize it. It's like how to. So I have. So it would be essentially the error between this distribution and this one. So we haven't. We didn't compute them, but like it seems.
Okay,
should
thanks.
be, yeah.
All right. Thank you very much.
Thank you.